In the last video, we defined projective space to be the set of linear subspaces of dimension 1 inside some k to the n plus 1. This was projective n space. And we saw that we can describe points in there by homogeneous coordinates, so by n plus 1 numbers, not all 0, which are unique up to scaling. In this video, we're going to see that affine space, as we know it, sits very naturally inside projective space. And for this, consider the map from AN to PN, a priori map of sets, which sends this vector here to the vector where you set the first homogeneous coordinate x0 to be 1, and then you just repeat the n coordinates that you have. The claim is this is a well-defined map, certainly, and it is injective. And to check this, well, if you have f of x equal f of y, then by definition, there's a scalar lambda inside k star such that lambda times this vector here, so 1, x1 up to xn, is 1, y1 up to yn. And if you look at this equality here, the first component of the equality tells you lambda is equal to 1. And then once you know this, well, lambda is 1, and so the comparing the remaining coordinates tells you each xi is equal to each yi, and so x is equal to y. So indeed, it's an injective map of sets. You can also describe what the image is. The claim is the image of f is just u0 defined as the locus of points inside projective space, such that the first coordinate is non-zero. That's a well-defined condition. This is independent of scaling, because if you have a point where the first coordinate is non-zero, you scale it by some lambda, it's still true that the first coordinate is non-zero. So that's a well-defined subset of projective space Pn. And to see that this is the image of f, you just see that this vector here, you can, as we saw in the example, you can divide by this non-zero number, and then this scales the first coordinate to be 1, and the others go to some numbers, like this. And then clearly this is in the image of this map here. Okay. So AN sits as this subset here inside projective space Pn. And what we did here, in fact, you can also formulate it explicitly by saying the inverse of f from u0, from its image to the to AN, sends this thing here exactly to these coordinates here. And then basically this here shows that if you compose f inverse with f, then you get the identity and similar in the other direction. Okay, so as an upshot, you think of AN as a subset of Pn. This is then often called the affine part of projective space. Now that we have this inside Pn, we can ask, what is the complement? What are we missing here? And well, this is of course Pn minus u0. So minus the locus where the first coordinate is non-zero. And well, the complement of that locus is the locus where the first coordinate is equal to 0. That's the locus of these points 0, and then x1 up to xn. And you still have the condition that this should not be the 0 vector. So in other words, this is now an element of k to the n minus 0. And the claim is, as a set, this is isomorphic to Pn minus 1, because this first coordinate, you can forget it, you know it's 0. So this operation here doesn't lose any information, and the remaining vector is non-zero. And then the opposite map would take this thing and just plug in x0 equals 0. And then this quickly shows that this is isomorphic to Pn minus 1. A priori, it's now isomorphic as a set. And once we put more structure on this, we will see this is indeed a homeomorphism, and indeed it's also a morphism of varieties later. But anyway, so somehow we see the complement of AN is Pn minus 1. And so we can write Pn as its affine part AN union this complement, so Pn minus 1. And this is then sometimes called the points at infinity. And in our picture here, kind of all the green lines going through this A2 essentially, these form this kind of A2 inside P2. And then all the lines which don't intersect this plane, which are kind of parallel to this plane, so for example, this line here, these form the points at infinity in this picture. Okay. And so I wanted to just show some few consequences and kind of generalizations of this construction of projective space, which use this affine space. The first one is a kind of shortcut, if you want, to defining projective space as a variety. Because what we have seen now is that U0, this locus where x0 is non-zero, this is isomorphic to affine space. But the zeroth coordinate here is not special in any way. So for any I from 0 to n, you can look at the set ui where the ith coordinate is non-zero. And then what you have, and then clearly by commuting the coordinates, this is also isomorphic to an. So what you get is the claim, and this we're going to use very often, is that Pn is actually the union of all these sets. Because any point in Pn, by definition, one of these coordinates is non-zero, and so it sits in the corresponding set ui. This is what we write here. And so we have a cover of this set Pn by these sets ui, and all of these sets individually are isomorphic to an. And what you can check is that the transition function which connect the ui to uj on their overlap here are morphisms. So in fact, somehow this here is an open subvariety here, similar there. And then the identity with respect to these identifications is a morphism, and they satisfy, of course, the compatibility because the identity composition of identity is identity and so on. And so from that, by the gluing construction, you get a pre-variety Pn with underlying set this projective space we constructed. And indeed, this will be the pre-variety that we get at the end of the, or somehow at the beginning of the next chapter, basically. However, as I said, we are, instead of doing this shortcut, we are going to develop a new language, homogeneous coordinates, ideals, and so on, for talking about projective space, and then define the structure of a ringed space on Pn by hand. And that will have the advantage that we then have all this language to help us. Okay, and so the last thing I want to show is that you can do this construction also with over specific fields. So for example, over the complex numbers. And then, I mean, we always get that somehow the field to the n, sorry, I guess n plus 1. So the field to the n plus 1 minus the origin always maps surjectively onto the projective space, sending this here to the corresponding point given by the homogeneous coordinates. And there's a surjective map. And what you can do then is, instead of looking at the topologies which we construct later, which have to do with cutting things out by algebraic equations, you can also just place on this set here the quotient topology by this map, the courses topology, making this thing here into a continuous map. And then the lemma, which is kind of nice, is that projective space with respect to this topology is compact. And that's very good because one of our motivations was that we didn't really get compact solution sets. And at least in the complex topology, it's very easy to see that this is compact. And so the idea how you show this is that inside of here, well, let's say, first of all, inside Cn plus 1, you have the unit sphere. So the points such that the squares of the norms of all the entries sum to 1. And clearly, I mean, the point 0 is not in there. And so this, in fact, sits in the complement of 0. So it sits in the domain here. It is compact because it's closed and bounded inside this thing here, which is basically a real space of dimension 2n plus 2. And the claim is the projection restricted to S is still surjective. And for that, you just observe that if you have any point inside the projective space given by some things which don't necessarily have norm 1, you can always rescale them by some real number until they have norm 1. And so and then this corresponding rescaled vector is a pre-image of the element of Pn that you started with. So this is still surjective. But then now we recall our topology lecture. So if you have something compact, then the image of this compact set is always compact. So if this is a surjective map, it means that this here is indeed a compact topological space with respect to this quotient topology. So you see over the complex numbers, this is a very nice space. And in fact, in differential geometry and so on, the projective space, either with a complex topology or projective space over the real numbers, this is studied a lot and has many nice properties.